we are back, about to go back into the program on this final day of the Humans to Mars Summit here in Washington, D.C. I'm Matt Kaplan, and next to me is
Beth Mund from the Casual Space Podcast. Hi, Matt.
Hi again. Very exciting. You got to talk, brought Cyan Proctor over to us. I finally got to talk to her backstage a few minutes ago. She was way too busy at Yuri's night, but we just had a wonderful conversation. So thank you for helping to enable that. What do we have coming up?
All right. We have the incredible Joe Cassady, who's going to walk us through Mars entry, descent, landing, and ascent.
First time ever launching a payload from another planet. It's happened from the moon, but not from a planet, and in this case it's Mars, because it's the sample return, those samples that are being collected right now by the Perseverance rover. So, and much more yet to come later today.
I'm counting the days. I can't wait to have a sample in the museums for all of us to see. A few years, what do you think?
It's going to be a few more years, I'm afraid, but it's all right. We're close. We're close. We are also not just close, but ready to go down to Artemis Westenberg, the what it would be President Emerita, I guess, of Explore Mars. So Artemis at the podium. We're ready for you to take it away.
Okay. Well, like Beth just said, Joe, the incredible Rocket Joe, will be leading this panel. And for me, Joe Cassady is, that I'm thinking good, reliable rocket engines, but I'm also thinking solar electric propulsion, and I'm thinking this man with 40 years of experience knows how, what the problems might be if you entry, descend, and land. It's, EDL, it sounds so simple if you say EDL, but it's actually, something to overcome. The heaviest stuff we've put on Mars are the Curiosity and Perseverance rover, and let's say they are 1,000 kilograms each. Humans we are putting on Mars will be at least 40,000 kilograms, their vessel, even if we send their food ahead and all the other stuff. So entry, descent, and landing is not a small thing, and then, taking off from Mars, again, not. So I'm very, very honored, very pleased to introduce Joe to you here. Joe, come out and introduce your own panel. And, tell us how we're going to fix this, how we're going to solve this.
Thanks, Artemis. Well, so yes, we're going to try to demystify entry, descent, and landing a little bit. And I want to thank Artemis for taking some of my introductory line about the great jump we have to do from what we've been able to do today with Curiosity and Perseverance with the Sky Crane, which was really when we first, we do the engines at Aerojet Rocketdyne for the Sky Crane. And when JPL first came up and asked us to recreate, and some of you may not know this is a fun fact, those engines are the same engines that were used for the Viking Landers. We recreated them without 18 separate little nozzles. If you look at the Viking Lander over here on the Mall in Air and Space, you'll see it had 18 separate little nozzles on each engine. That was to keep it from disturbing the regolith, because we had no idea what Mars regolith was like, and we didn't want to dig a big crater because we had a scoop that we wanted to use on Viking to look. Somebody mentioned Gil Levin's biology experiment. Anyway, we recreated those for the Sky Crane, but when JPL first came and asked us and told us what their idea was for the Sky Crane to get 1 metric ton down to Mars, a few of us were like, really? You're going to lower it down on a tether? So, we've gone to some pretty extensive lengths to just be able to get 1 metric ton down. As Artemis says, now we've got to make the jump to 20 metric ton class payload. So we've got a really great panel today to talk about that. So let's kick off with, first of all, Doug Trent. Dr. Trent is the Acting Space Systems Team Lead for the Advanced Concepts Office at NASA's Marshall Space Flight Center. His primary duties include the Entry, Descent, and Landing and Ascent Lead for the Exploration Systems Development Mission Director at Mars Architecture Team, as well as being in support of the Human Landing Systems Architecture and System Analysis Group. Doug joined NASA in 2012 as a co-op student while he was working on his graduate degrees within the Aerospace Systems Design Lab at Georgia Tech, Rambling Wreck. He earned his bachelor's in his bachelor's in mechanical engineering from Cal State University, Sacramento in 2011, as well as a master's and PhD in aerospace engineering from Georgia Tech in 2014 and 2017, respectively. So I'm going to turn it over to Doug to talk about EDL.
All right. Thanks, Joe. I want to start us out with basically a kind of high-level discussion in terms of entry, descent, landing, ascent, and how introducing humans into those systems can really impact the design of those systems. So next chart, please. All right, so Mars poses many unique problems, especially for getting humans there in human spaceflight. So obviously, there's just the sheer distance. It's the furthest. Humans have never traveled that far in space, and so it's just going to be exponentially further. There's obviously the time away from Earth. We heard in our previous panel this morning, there's a lot to consider in terms of mission duration and how that's going to impact things. I will touch a little bit on that in terms of how that impacts the EDLA systems. And then, of course, one of the other very large and unique problems that comes in is entry, descent, landing, and ascent for humans. And so obviously that's going to be the focus of what I'm talking about here today. So next chart, please. So you can't really talk about EDLA and EDL on Mars without acknowledging the fact that we have a very long history with robotic missions to Mars and robotic missions performing EDL on Mars. You will note, as you can see here, the right-hand side of this image is basically all of the missions to Mars globally, not just NASA, and how they fared in mission success. So the first 40 years, you can see, is a little bit storied. They had 3 successful landings, and you had 7 not-so-successful landings. Those 3 successful, of course, were Viking 1, Viking 2, and Pathfinder. Now, of course, if you fast forward that into the last 20 years, it's almost a mirror image of what we saw in the first 40. You had 7 successful landings, and you only had 2 failures or partial failures. And so that's fantastic that we've been able to progress that far in developing our technology and our systems to increase the reliability and the successfulness of these missions. However, obviously, I'm here focused on the human aspect. And whenever we're considering human spaceflight endeavors, typically safety and reliability tends to be one of our top metrics in terms of ensuring that we do have reliable and safe systems for those humans, because obviously we do not want to lose them at all costs. And so with reliability, even as what we've seen in the last 20 years for EDL, that's frankly not quite at the level that we would like to see if we're going to commit to putting humans on these systems and sending them to Mars. And so there's going to have to be a shift in terms of increasing that reliability and safety to levels that frankly any organization would be comfortable with putting humans on board and sending them to Mars, because obviously the humans are some of our most valuable payloads and we want to ensure their safety. So next chart, please. So now this chart, it's a lot going on here, but basically it's looking a little bit more at the technical performance in terms of EDL. And so you can see here the big picture is there's been a steady progression of really what I call in-family EDL development. So you're getting increased mass to the surface of Mars, as we've talked about, starting with Viking 1 and 2, all the way up to most recently Perseverance rover landing roughly 1 metric ton on the surface of Mars. You've also had a steady progression in terms of the precision of the landing. You've gotten those initial landing ellipses where your targeting for your landing has gotten significantly better by employing various different technologies, but they've all been relatively in a similar class, using parachutes, ballistic guidance. Obviously, Perseverance did introduce and successfully prove out the terrain relative navigation technology, which is fantastic and something that landing humans on Mars is obviously going to need, and so we're very, very happy to see that development. But then, of course, if you look at the far right for human-class landers, as has been alluded to several times already, there is a paradigm shift needed to be able to get this class of lander to the Mars surface. 20, 25 potentially tons of usable payload on the surface. You're looking at, when you include the dry mass of the lander, you're looking at 30, 40, potentially more tons of mass that you got to put down on the surface of Mars. And this is just orders of magnitude, or at least one order of magnitude greater than what we've done in the past. And so there's going to be, some significant new development that's going to have to occur to enable that ability. So, for instance, things like the diameter of the lander. All the previous landers you can see there, they've been rigid bodies. They fit within roughly a 4.5 meter constraint for the launch vehicle fairing. When we go to these larger systems, you just need more surface area to basically do some of that initial slowing down through your entry, and that needs a larger diameter. Well, we don't have launch vehicle fairings that are 16, 19 diameters, or 16, 19 meters in diameter, and so you have to start looking at alternative technologies, potentially deployable decelerators and things like that might be able to help you. Because unfortunately, some of the technologies that have been well proven out through our robotic exploration efforts, like the parachutes and things like that, don't really scale well when you go to these scales of mass. It's just the parachute begins to be very difficult to build at those scales. So that was mass. Obviously, mass and mass down is a big thing. The other component is precision. So in terms of the precision of the landing, again, we've seen a very good progression of that precision over time, but supporting human landers, we're looking at, again, another order of magnitude increase in the precision of that landing, maybe down to about 100 meters in accuracy, as opposed to maybe the 7 meters or 7 kilometers that Perseverance had. And so that comes, again, we're going to have to look at new technologies that need to be developed to be able to achieve that capability. Things like direct force control during your ballistic entry, so a different guidance mechanism. So you're going to need potentially deployable decelerators like our HIAD or hypersonic inflatable aerodynamic decelerator. Supersonic retropulsion is another potential technology that you might have to employ if you're not able to use parachutes and things like this. And then, of course, terrain relative navigation. We've already done some initial development of that, and demonstration with Perseverance was fantastic, but there may be additional additions to that technology that may be needed to, again, achieve these precision. And now, a lot of people might ask, well, why do I need so much mass to support humans to Mars? And really, the big component is space is a harsh environment. Mars is harsh as well. Humans don't like living off of Earth very well. So there's just a lot of systems that we have to take to be able to support humans. You need food, you need water, you need air, so that requires an environmental control life support system. Typically, they're going to need somewhere to live, some habitation or something to live in. Typically, if you're going to Mars, you want to do some science, some cool exploration. You're going to need mobility, so maybe rovers, EVA suits, and all of this comes at mass. And then, of course, if you have all those systems, you got to power them. So there's more mass, and so you can just see how this cascades into this, huge mass that we are going to need to deliver. All right, next chart, please. So I focused a lot on EDL, and of course, part of the other name in this panel is Ascent, and so I do want to take a little bit and talk about Ascent. So humans, hopefully not much of a surprise to folks, have only ascended from 2 celestial bodies, Earth, and we've done it hundreds of times, and the Moon, we've done it 6 times, although we're hoping to increase that number on the Moon in the near future. Stay tuned. So, like I said, Earth, we've done that hundreds of times. It sounds like it's a trivial thing now. We tend to make it look pretty trivial. But in fact, there is a lot that goes on under the surface to be able to achieve those human launches. There's huge amounts of support that go on here on Earth, both equipment, ground support equipment, and also personnel, technicians and engineers, supporting these systems before they perform their launch. You also have generous delay and abort capability. So if I have a weather event or if I have a technical issue with the vehicle, I can scrub for the day, I can send people out there, figure out what might be going wrong, and then make another attempt later. Typically, you're not going to have a risk to the crew. There might be some mission delay or loss of mission with that, but it's not going to be a loss of life kind of situation. For the Moon, for at least the 6 times that we have ascended from the Moon, the vehicle was delivered fully fueled and prepared for ascent. So there wasn't really that much activity that had to go on in terms of preparing this vehicle for ascent. It was fully fueled. Basically, they could land and probably in a relatively short amount of time be able to take off if there was any issues. They also had real-time ground support via communication. So Earth to the Moon is relatively close speaking, and so communications don't have that much of a delay, and so they can get real-time communication with, say, ground control in terms of if there's any issues, but also in terms of just general operations of, hey, this is where we're at in our mission, and you need to be getting back inside the system and buttoning up and getting ready to go. And so that obviously gives you some operational flexibility and capability there. Now, when you go to Mars, a lot of these things I mentioned aren't necessarily in place. And so, for instance, you have little to no margin for delay. So on Mars, if I'm looking to bring my crew back up, if I hit the go button and it does not go, there's a lot of implication there. I don't have all the humans that are here on Earth to be able to support troubleshooting and things like that. Also, if there's any kind of problem and we can't figure it out, the crew can't just sit around and, oh, the mission is scrubbed. We would lose the crew, and that would be an absolute travesty. And so we obviously want to avoid that at all costs. Second part, little to no real-time ground support in terms of communication. So again, like I mentioned on the moon, they could talk relatively, real-time in terms of any operations. But with Mars, because again of the sheer distance, you've got anywhere between 20 and 40-minute round-trip communication delays. And so if there's an issue, it could potentially be upwards of 40 minutes between Houston, we have a problem, and Houston acknowledges.
Yeah.
Now we have to start troubleshooting. That could be a big challenge in terms of operations. And then finally, for Mars, a lot of the architectures that have been considered, the vehicle may likely arrive unprepared for launch. So it might be defueled for mass delivery reasons, and so you might have to do ISRU to refuel it, or you might deliver fuel some other method and transfer it into the vehicle. And so, of course, that takes time, and so this vehicle may have to be delivered prior to crew arrival. And so now you've got all these new situations of, well, I've got to and place that asset, I've got to do a bunch of work to get it prepared, and it all has to be done robotically because I don't have humans on Mars already to kind of help out with these systems. And it'd be kind of equivalent to rolling out, say, a vehicle from an assembly building here on Earth to the pad, and then not having it fueled and basically having it sit out there on the pad for multiple years before I have to launch it. I mean, that sounds crazy to probably most launch vehicle providers today, but that's in essence what we're going to have to do with a MAV in certain architectures. And so obviously, I've been talking about a lot of the challenges with humans and introducing humans into these EDLA systems. And I do want to say, yes, there are a lot of challenges, but we are actively working on these. And there are things that we're thinking about right now so that when the time comes, we'll be ready for these challenges and we can solve them. They're absolutely solvable, and we are working on these. So last chart I got, I just want to leave us with this gorgeous image of basically the evolution of a Martian. Starting on the far left, you got Pathfinder, Spirit, Opportunity, Curiosity, Perseverance, and Ingenuity. And then, of course, looking to the future, you've got Mars Sample Return, and obviously what we're all here to talk about, humans on Mars. And with that, thank you.
Thanks, Doug. All right, well, that was a great way to get us started and kicked off. And you heard Doug mention a couple of times there the importance of precision landing. And Artemis referred to the need to have, the support equipment and things like that pre-positioned. And I think almost all the architectures are looking at that. So obviously, you don't want the crew to have to traverse multiple kilometers to go get the stuff they need or to even make it to their habitat when they land. So that's the real criticality of being able to do these pinpoint landings. And to tell us a little bit more about that, we have Phil Hattis from Draper Labs. He's a laboratory fellow at Draper. He came there as an MIT graduate student and continued his career there ever since. I'm seeing a trend here. He's been a technical director for launch, space, missile, aerial, and soldier system development programs at Draper. This included work on human-rated space systems and lunar and Mars landers. He also served for 4 years on the Air Force Scientific Advisory Board. He's a fellow of the American Institute of Aeronautics and Astronautics and a past AIAA Vice President for Public Policy. So, Phil, over to you.
Thank you, Joe. So what I am going to talk a little bit about is, as was mentioned, the precision landing issues. Back in the early 2000s, the concepts at that time for the sample return missions would have required the collection vehicle arrive within a couple hundred meters of the vehicle that had cached the samples. The current mission, you'll have a more capable rover to move, but that wasn't the case at the time. So we were still looking at the 1,000 kilogram class vehicles, and we're looking at precision. We spend a few years looking at the alternatives for that. But when I go through my observations from that, I'm going to extrapolate to some of the things that were discussed when you go to the human mission, which is going to be much bigger. So next chart, please. What are the factors that impact the landing precision? Well, there's the approach navigation, state accuracy, how well you know where you are when you get, as you're getting toward the planet. Map tie errors, where exactly are you going on the surface, and how well has that been related to inertial space? The atmosphere will have density variations. When you go to some kind of aerodynamic decelerator phase, there'll be wind drift. If you put control in there to try to deal with these things, there's mass cost associated with that, and there's realizable time response to any steering commands you have that limits what you can do. So I'm going to go into those things a little bit more. Next chart, please. So looking at where we stood, Perseverance being the recent architecture, during the approach phase, you are doing radio and optical-based navigation, the radio navigation being from Earth, the optical-based navigation being done from on board the spacecraft. You then hit the atmosphere, you have the entry phase, they do a bank to steer with a rigid, somewhat asymmetric conical body, and with Perseverance they demonstrated the capability to get an accuracy by the end of that entry phase on the order of 2 kilometers. Then you deploy the parachute. There is no guidance and control during the parachute phase. You have imaging that they pick up. At that point, you've got an altimeter doing the navigation based on atmospheric pressure and radar both. And somewhere partway through the parachute phase, they began to do the terrain relative navigation. And what were they really trying to do with there? They were trying to avoid obstacles. They had a 7-kilometer footprint. They weren't saying where they were going in there. They just wanted to be sure they landed somewhere in that footprint and it was a safe spot. So going from the 7 kilometers down to the 100 or 200 meters is where all the challenges are. Next chart, please. So what do we have to do to accomplish each of those things? The optical aiding during the approach, you take images of the planet limb and the stars relative to the planet limb. This is a capability actually devised originally using human eyes as a backup system for Apollo. You then do final mid-course correction burn to correct your entry interface based on any errors you see at that point. And the image processing is neat in that you've got a day or two to do it. There's no time critical, there's a turnaround that you have to live with, but the time criticality is not an onboard system processing concern. On the other hand, when you start doing the landmark tracking, either from orbit or during EDL, orbit being if you happen to go to orbit first, like you might do with a human mission, you are utilizing images of surface feature positions and the relative orientations along the vehicle track to do the navigation. That permits you to take out the map tie errors because everything now is becoming relative to the surface rather than to inertial space. But particularly during the descent, including what they did in Perseverance, the image processing is very time critical. At most, you have seconds to convert that image into a navigation update. And that usually means that you're going to have a separate dedicated processor, and you're going to have some very clever processing algorithms to do that. And the more sophisticated you're trying to make that for navigation and not just for obstacle avoidance, the more challenging those processing constraints will become. Next chart, please. And then the drivers that we haven't dealt with to date, to a great extent. The atmospheric density impact. Well, your deceleration, including during the entry phase, is going to be affected by that. Dust storms change the construct of the atmosphere. So you have to be able to account for how your deceleration for the whole profile is going to be altered by that. That really means to achieve true consistent precision in that phase, we're going to have to not just forecast what the atmosphere does, but probably have some into observation. Because the construct in a particular dust storm, as was discussed earlier this morning, can be very different than another dust storm, and so you can't go very well by past history to determine how the density will vary. Wind drift, you can get some pretty darn high winds laterally in the atmosphere, and the dust storms can actually make that worse. If you can forecast that, a certain amount of that is seasonal. You know, as the poles start freezing out carbon dioxide, you get winds that compensate for the change in the density of the atmosphere. So some of that we already know how to predict, but there's other factors, like, you know, as with the dust storms, where we would need to probably get in situ measurements. But you take that together, and with what you're able to do to forecast, whether it's a long-term forecast or short-term forecast, is you bias where you're targeting the end of the entry phase, so that during the parachute descent, the wind drift you're going to get will take you back approximately to where you want to be.
Okay.
And then the uncompensated part of the wind drift has to be taken out during the powered descent. And that can be very costly.
Yes.
Next chart. So the design considerations you have for actively managing that, we looked at parachutes and inflatables that had some asymmetric geometry that could deploy at Mach 5 or Mach 6 instead of the Mach 2-ish range where the parachutes now deploy. With parachutes, you can pull on various edges and get what's called slip by skydivers.
Oh, right.
And that can be used to maneuver around. The problem is that Mars' atmosphere density is very low. The amount of entrained mass in the canopy is a lot lower than you have on Earth. So what we call the mass ratio, which is the ratio of the canopy mass to the entrained air mass, is sufficiently lower at Mars that the control response time when you do slips is about a factor of 5 slower than it is on Earth. And you get a mass penalty for putting those actuators on. Right. But it does buy you something, because what errors you have at the time that you ended entry, you know, particularly if you have terrain relative navigation at that point, and that can be taken out with a few actuations you may get in that 110 or 120 seconds that you have under the parachute. If you go to an inflatable design, you've got two options. I mentioned here, you know, you can rotate to the asymmetry in order to move your lift vector. The other option is that you can put actuators in there that change the shape of your configuration with time. That tends to be more mass intensive than to do that. Both, because of the scale of what we're talking about, both of those tend to have a significant actuation time. So they may be somewhat better than the slip I was talking about for parachutes, but you're still going to get a rather slow actuation time. So the issue is, yes, those are good ideas if you can afford to take the mass penalty. They remove some of the errors. You still have to bias for the wind, but you really want that wind biasing to be as good as possible, because when you get to the powered descent, if you get to the point where you have to take out more than 1 kilometer lateral error, you could spend more propellant going sideways than going down. And that is a huge penalty. So the bottom line is we really have to work first on better understanding the density variations and on much more accurately forecasting the winds, probably having in situ assets to support that, and then constructing the entry profile and the kind of actuation that we use to remove as much of the error as possible before we go to the propulsive descent. So those are my main points, and we can elaborate as appropriate point.
Thanks, Phil. That's fascinating. Yeah, and I just think of all that Phil was describing, and you've got a rather sluggish system that you're trying to control. And remember, this is 7 minutes of terror, right? So you don't have like an infinite amount of time for this thing to do what it needs to do. All right, well, let's go on then to the last part of EDLA, the A, and that's what David Murrow's here to tell us about. So Dave is the Senior Manager of Deep Space Exploration Strategy and Business Development for Lockheed Martin Corporation Space. In his current role, he's responsible for positioning the company to support NASA robotic mission or exploration missions in planetary, lunar, astrophysics, and heliophysics arenas. He's focused on extending Lockheed Martin's proven heritage in robotic and human spaceflight. They had a few of those successful landings on Mars, I'll point out, into the next phase of exploration missions. So Dave, over to you.
Great, thanks Joe, and thanks Doug and Phil for the great technical discussions. I learned a lot. So I'll talk today about mostly the Mars Ascent vehicle because, as has been said, that's the first time we're doing this. We were lucky enough to be the first landing on Mars with Viking way back in the past when I was still really little, I had hair. So we're doing it again. This is the first Ascent. We hope it's not 50 years between the first landing and this, or the first Ascent with the robots and the human Ascent. So we think we're on a faster pace. But we're going to prove things at a robotic scale. So let me walk you through, these are sort of NASA charts that everybody can see, but let me give you a little color commentary on how the Mars Ascent vehicle works. As we go through it, I'll try to point out some things that will and may not scale for human systems. So the first thing to say is that the kind of initial condition for the ascent of this vehicle is that it's safely on the surface. You just heard from Phil and Doug a lot of the considerations for getting down. For this one, it's about a 1.5 metric ton or 1,500 kilograms going into the atmosphere. So it's not that, we don't have that scaling problem up to 20 to 40 tons like Doug talked about, but we do in fact have a bigger system than we have for Curiosity or Perseverance. So the Mars Ascent vehicle is the main payload. You can see it there, positioned on top. We call the cocoon that it's in, we call it a cocoon or an igloo or something like that. Basically, it's very well protected. This is, as a difference from the human missions that we launch from Earth, this is different because the thing is actually protected in this thermally protected container the entire time. So the good news is you've got it protected, you've got it environmentally controlled, unlike a rocket that's on the surface of the Earth and, you know, in Kennedy Space Center with lots of sun and wind and rain and lightning. This one is somewhat more benign environment controlled inside the igloo. However, the bad news is it's got to get all the way to Mars. So not only does it have to have a safe EDL, as you heard these gentlemen describe, but it also has to handle the vibration and thermal extremes of launch and cruise to Mars, all buttoned up in the aeroshell. It's got to handle all of the extremes of the shock from the deployments of the leg and the deployments of the parachute and landing on the surface. And then it's got to be fully functional from the get-go. So once that initial condition is met, you can see there that the MAV is sitting, as I said, inside its igloo with the igloo cap off and also the nose cone cap of the MAV also off as well. And you can see, I'm not sure if you can make out on the chart, but that is what we call the orbiting sample. I'll use that term a couple of times. OS is what we use for shorthand. We'll probably come up with a better acronym, but for now that's it. OS is what the payload is called. And that's a little, you know, sort of basketball-sized sphere that has all of the samples placed in it from Mars Perseverance. Now we'll put those in. You can see a little robotic arm there off to the right-hand side. We'll grab those samples off of the sample fetch rover that the Europeans will drive over to us. We'll grab those and we'll put them one by one into that nose cone, into the OS. Those have to be precisely placed, and there will be a certain sequence because, of course, the mass of this vehicle matters a lot, and not just the mass, but how that mass is distributed. I'll talk a minute about the upper stage, but as a spinning vehicle, imagine a football. I'm a football fan, so I always like to use, well, let's see, for you, Phil, it'd be Tom Brady. For me, as a Denver guy, it'd John Elway or Peyton Manning. But I like to use a football as an analogy. You have to have that thing properly balanced so that the spiral is a nice tight spiral and it gets to the receiver properly. You don't want it imbalanced or the thing is going to wobble like, well, say if Phil or I threw the pass. So then you're going to fold up that nose cone and get ready for launch. Let's go to my next chart. And this is the launch of the vehicle. This is, again, a NASA graphic. You saw the other day with the chart or the demonstration that Jeff Gramling showed you, what happens between that first picture and this one is that the MAV actually the cocoon gets opened, the igloo gets opened, and then through a system called Vector, which is a backronym for vertically erected or something like that. But Vector is the system that sort of throws the thing up in the air. So it throws it up in the air, similar to the way some of our missile systems here on the Earth work, throws it up into the air, and when it's at the proper attitude and elevation and time, the solid rocket motors are ignited, and that's what you see there, right after the solids ignite and it's on its way to orbit. So again, going back to the system and what scales and what doesn't to a human system, I doubt if we're going to put the humans in a horizontal vehicle and throw them up in the air and then ignite it. So that's something that'll work very well with sort of smaller missile-based technology for the Mars Ascent vehicle, but that'll be a challenge when we go to a human-scale vehicle. We're bigger than those little sample tubes. So here's the Mars Ascent vehicle. That's the first stage. Like I said, it's a solid rocket motor. It's a thrust vector controlled system. So at this point, it's just inertially pointed with the TVC system on the back, taking it through the first stage of its ascent. Next chart, please. This is after it's basically in the coast phase, after the first stage is burned out. So that bottom half, the orange there, that part is now burned out and the spacecraft is coasting. What happens during that phase is that the first stage separates and falls off, and then the second stage, which is all initially guided by the pieces that are inside the silver, that's the so-called interstage. That's where all the computers and all of the guidance and the reaction control system. I know Aerojet Rocketdyne is likely to provide some of that hardware, no guarantees because it's all an open procurement. But
fingers crossed.
I have to give a shout out to the entire industry base. And frankly, this is a bit of a diversion, but we can't do this alone. Lockheed Martin's really proud of having a role, but NASA needs help. We need help. The industrial base, we need your help. This is a big team effort. Anyway, the interstage falls off, and then you can see those sort of white fins up there. That actually contains the spin-despin motors. So first, the spin motors fire up, spins up that entire upper stage, so that, as I said, it's a Peyton Manning type pass, and it ignites the solid rocket motor, very well balanced system, and takes it all the way to orbit. Then the other half, so there's motors in those little white fins that point both directions laterally. One spins it up, the other spins it down, so that it despins, and then it's separated from the rocket. So the OS, now this basketball-sized container, is with the samples, is in a free orbit around Mars. Next chart. So this is a chart of right after that second stage burns out, and now the OS has been pushed off. Believe it or not, the mechanism, it's a pretty complicated mechanism that pushes that OS off. Believe it or not, it's called adios. So the spacecraft, the rocket, I kid you not, NASA's very good at these acronyms.
Yes.
It's
the national acronym in Space Agency.
Thank you, Joe. So the second stage, adios, pushes the OS off, and now it's in orbit. Now, what we've done with the second stage is we've tracked that with a radio beacon, and so we understand the exact initial conditions when the os is pushed off. So we take that and we add to it the precise amount of velocity that's added by Audios and the springs, and then we can propagate that orbit forward. So it's really important to do that because obviously the Earth Return Orbiter has to come, and it's the active system. The os is purely passive at this point. The Earth Return Orbiter, which I think if you go to the next chart, I show a picture of the ERO coming towards the os, and it's the active system. It has to go up, find the os, home in on it, and essentially it's like, imagine a basketball hoop going after the basketball. Instead of the other way around, you're actually taking the hoop and moving it towards the basketball. So we bring that thing into the Earth Return Orbiter. We talked a little bit about planetary protection, and this is something, again, that it will have to be done with humans, probably not with the method that I'm about to mention. The os is actually moved through the system, and a welded shell is put around the os to do what we call break the chain between what's on Mars and what'll be on the Earth. That chain, that mass, that contamination, if there is any, won't be released until we're in a biosafe facility here on the Earth. So humans, maybe we'll learn about Mars sample return, we'll learn about toxins. Let's hope we don't have to break the chain and weld the humans in place. So the os goes into the ERO, and then, so I'm pretty much done with the Mars Ascent vehicle, but I think I do have one more chart which shows the exciting part. So next chart, please. Oh, I guess I left that chart out. The next part is when the os gets actually that top little piece with the gold blanket on. That's called the Earth Entry System. Gets pushed up into the Earth Entry System, and then that gets released from the ERO as it flies by the Earth. So we will fly that into the desert in Utah, very similar to the way we've brought back samples from Bennu. Will be coming back samples from Bennu will be coming back from OSIRIS-REx later this year. We've done samples with comet material and also solar wind particles, stardust and Genesis. So that's a pretty well understood part of this. And on this one, it'll be purely passive, no parachute. So we won't have wind slip on that piece of the mission. So that's the Mars Ascent vehicle. Lots of things that we're going to learn. And as you can see, some of them, as I've tried to point out, I really wasn't trying to get you to laugh, but as I've pointed out, some of these things really apply very well to the human mission, but some of them, frankly, don't. And so we use what we think of as sort of missile technology and missile analogies for the MAV because it's from me to Joe. It's about 3 meters across. So a missile kind of works. But with a launch vehicle, with humans, there's a lot of stuff that we're going to have to learn all over again, including some of those guidance systems. We won't put the humans on a spinning upper stage. So some of that guidance will have to be relearned. So there's a lot of challenges ahead of us. We're happy to be building the first one, and we expect to learn a lot of lessons from that and apply them. But we're going to have a lot of future lessons and a lot of future design. Look forward to working with Marshall on that, as well as working with Marshall on the MAV. So thanks for your attention, and look forward to your questions.
Thanks, Dave. So I'll go ahead and lead off with a couple of questions, but I would encourage folks in the audience, if you have questions, to come on down and just stand by the mics there, and we'll get to you. It's pretty hard for us to see you out there, but we'll notice if you come down front. So first of all, let me start with Doug. So we heard a lot of very interesting things here about the whole process and the scale up of EDL to the human scale that we're going to need, and then the very intricate challenge of precision landing. So my question for you, Doug, is between EDL, entry, descent, and landing, and Ascent, which phase of the mission concerns you more and why?
Yeah, that's a great question. Obviously, like you pointed out, there's lots of challenges with entry, descent, landing, and Ascent, both components. For me, I would certainly say Ascent is the one that I would have more concerns about and more things that I want to ensure go correctly. And the reason for that is with entry, descent, and landing, if there's some issue with the system before I initiate EDL, I can find that and I can scrub my mission. I don't have to go to the surface. Yes, it's a bad day, but at least I can default maybe to an orbital mission and then bring the crew home safely. With Ascent, after I've already done my EDL phase and they're on the surface, if I have a failure with my Ascent system on the surface and it's something that I can't detect before I send the crew down, because obviously I'm going to go through a whole effort of ensuring that system is prepared for humans before we send them down. But there's always the potential that something I can't detect remotely has gone wrong with the vehicle on the surface, and then once they're already down there, if that issue were to arise and they couldn't descend, you're now in a loss of crew situation, which again, getting the crew back is one of the most important things for us. And so ensuring that that system is reliable to the most extent possible is going to be critical for a crewed mission to Mars.
Yeah, Phil, yeah.
I'd like to add a little bit.
Sure.
You know, Doug, you're focusing on what could happen before the event.
Right.
One of the things I've worried about over my career is mid-event abort scenarios.
Mm-hmm. Oh, yeah.
And almost nothing that we did for Apollo would apply here. You know, with Apollo, or what we're trying to do with Artemis, you can try to do a descent abort at almost any phase until you're within a small number of feet of the surface of the moon. When you talk about the kind of sequences we've been talking about entry, that is not an option here. So we have to come up with strategies for what constitutes a safe recovery process if we have a major problem. And that's true for descent or ascent, though in the ascent case from Mars, that's probably a little bit more similar to what would be needed for Apollo and Artemis and for the landing.
Yeah, Dave, did you have something to add on
I
that
just
too?
wanted to make a comment about kind of the operational aspects of both EDL and Ascent at Mars. Right now we have systems that are robotic. We use pre-programmed sequences with lots of different fault trees for different failure scenarios and all of that sort of thing. So we think we understand how to do a sequence at Mars with a robotic system. The way we use human systems, though, is that almost everything is very tightly scripted. And the fact is that we may not be able to script things nearly as accurately because things are going to happen in whether it's fueling the rocket, like you guys mentioned,
right,
or whether it's some entry, descent, landing scenario abort. Our astronauts are going to have to be much more active participants in the mission than perhaps we're used to now. We have a lot of simulation to make sure that the astronauts have so much safety, and it's not that they're not thinking and participating, obviously, but they're thinking and participating at a level which is different than releasing a huge amount of explosive energy in a precise direction during ascent. So there's a lot of operational things that we have to worry about. We've conquered those with some of our robotic missions, but moving to a light time delay scenario where the astronauts really do have to be on their own, that's going to be something that we're really all in kind of a new phase for us.
Yeah, good point. Well, let me turn to you, Phil, and I'm fascinated by the amount of variables that seem to be there. At Mars, and you're pointing out, quite a bit different than what we have to deal with trying to land on the moon. So, for precision landing, what capabilities still need to be advanced to enable us to do precision landings on Mars?
Well, I'll just elaborate on a couple of the things that I started to mention, but you need better real-time knowledge of the density and the winds. And the way you would achieve that would almost certainly be with some kind of in-situ resources. The density can probably be determined from an orbital platform that is looking at the energy balance of the atmosphere and relating that to ever-evolving and improving models of how that energy balance, particularly with various levels of dust and train to the atmosphere, changes that profile. The seasonal effects we probably understand reasonably well. We can improve on that too. As CO2 freezes and thaws and takes out and puts back some of the atmosphere at the poles, you've got the movement of the gas between those. So that part we can deal with. But winds are driven by so many variables, and the day-to-day variation of the flux of the dust in a dust storm, change in the amount of solar radiation hitting the surface and the amount of thermal energy pushed back in the atmosphere, that can drive significant changes in the winds. And there really hasn't been a lot of work done on this, and work should be done on what kind of in situ resources, probably surface and orbital based, can collectively come up with better wind profiles. What we do on the Earth when we're worried about a launch, we can put up a balloon.
Right, exactly.
That's not really an option
right.
in Mars.
And we've just recently seen a couple of crew returns from station get delayed because of weather conditions in landing zones. So we're always monitoring weather. It's a real situation even for coming home from low Earth orbit.
But we need, probably, there's be various types of laser profiling. We have to have the equipment situated so it doesn't become, in various locations, so it doesn't become completely blocked by whatever dust burden is in the atmosphere. So it's not a simple answer, and there's probably no getting away from having some in situ support.
So you're saying we need some assets there, right there on the planet to aid us with that?
I think so, yeah.
Yeah, okay. I want to do a little bit of a follow-up on that one and throw it open to the whole panel. Mariner 9, I think it was, we launched, and when we arrived at Mars, there was a global dust storm going on. So initially, everybody said, "Oh, Mars looks very different than we thought it was going to." You can't see anything. In Vikings, we put the spacecraft into orbit, and I remember, I think on 2 or 1, there was a delay in the actual landing attempt because they wanted to wait for conditions to improve. So my question is, rather than, as we've done with our recent probes, go directly into entry, descent, and landing, is there any advantage architecturally to going into orbit first so that we could assess those conditions before we attempt the landing? Thoughts on that?
I can go ahead and start us off on that.
Sure.
I mean, I would say yes, there are some advantages operationally. Obviously, it gives you a chance to kind of take a breath and check out your systems, ensure that they are as ready as you can be for performing some of those critical phases of the mission, entry, descent, landing. So that obviously from an operations standpoint is great. In terms of, if you're going to try and wait out a storm, I mean, if it's a global storm, they tend to last a lot longer than maybe some of the potential missions that NASA is currently considering. And so that could be a challenge there where, if we do really want to go to the surface, maybe I will try to develop technologies and systems that might be able to weather the storm, for lack of a better word.
Yeah.
So that we can go down and potentially do those missions still with that weather concern.
Right.
But, there potentially could be the option that if the storm is bad enough, and our mission is not designed for a really long duration, or we can't wait it out in orbit.
Your short stay,
Right.
you lose your window to get back.
And so, depending on how you plan your mission, that could result in a loss of mission situation. Now, granted, not a loss of crew, which is always a good thing. We want to bring our crew back. But yes, there's a lot of thought that has to go into ensuring that we can achieve that mission under all these variables that we have going.
Yeah, I'll just follow up a little bit with that. We put, we're lucky. We have people building Orion now. We have people building Mars spacecraft. We put those guys in a room about 3 or 4 years ago and came up with this concept called Mars Base Camp, where we sort of tried to think a lot of that through. And the first thing that I'll say about Mars Base Camp, and I think Christy Edwards, who's probably still in the audience, presented that the other day.
She did, yeah.
The first thing I'll say about that is that it's a lot of mass.
Right.
But in terms of an exploration scenario, one way to do it is to put something in orbit with 2 Orions so you can come back, and propulsion modules, living space, all of those things that you might need for the time that you're cruising to Mars. And then while you're in orbit, that's when you would take the time to assess whether or not it was the right conditions to go down. We actually call in that Mars Base Camp, architecture, we call those sorties, because really we think of that as the base camp, the analogy being Everest Base Camp, and the sortie is to go to the summit and then you come back down. So that's one way to explore Mars. Potentially with drones and helicopters and that sort of thing, we might get a different global view than just putting astronauts, one place. So there's a lot of different exploration architectures that we could adopt to take humans to Mars. The fun part of a conference like this, and the fun part of the next 10 years, maybe more, hopefully not more, is that we all get to participate in designing these architectures and thinking these things through, because these really are human factors that we're talking about, and guess what? We're all humans. So we need your help.
Yeah. With that, I'm going to throw it over to the audience. Yeah, let's.
Oh,
I got somebody behind me already? Okay, well,
but
can we take a few
I
questions?
cannot resist these questions. Go right ahead.
Okay, please.
Lucy, are you first? You can have the first question and then Lucas.
Where will humans land on Mars?
Could you say it just a little bit louder?
Where will humans land on Mars?
Where will humans land on Mars? Okay, panelists. Any votes?
Well, there is, to date, we've tended to always go to locations that are below the Martian mean altitude because we get more atmospheric deceleration opportunity by going deeper into it. I don't know how high we can go. One of the things, they've been trying to design systems so that they can go higher, but I think, for the foreseeable future, there'll always be advantage to going to parts of Mars where it's below the mean.
Okay, so someplace low-lying on Mars is our thought there. Lucas?
I want to do Ascent from Mars, and specifically on things like sample missions and also humans. But what degrees and what colleges would you suggest for that?
I have a vote, but I'll let these guys go first.
I think you guys just found your intern and your future pipeline there.
Yeah.
Well, I'll start out and just say, before you start thinking about what colleges and degrees to go for, first, keep this excitement you have for Mars and study math and science. Because mathematics is really the tool set that allows you to become an engineer. And mathematics also, because I'm in the private sector and we like this thing called shareholders and profit, mathematics is also really important to making a business run. And we talk about commercial being involved. The business has got to run, and so spreadsheets, financial analysis, so pay attention to your mathematics, and almost any degree is going to be valuable to the overall thing. This is going to be a big, big endeavor for all of humanity.
Okay, do we have one more question over here? Yeah,
Thank
go ahead.
you.
Thank you, Lucas.
Yeah, can you hear me?
Yes.
Yeah, just kind of a elephant in the room question.
Uh-oh.
I just assume that you guys in EDL and sample return don't have an established link with human missions to Mars in a day-to-day basis. And the reason I'm mentioning that is because optimistically, the earliest humans will be on Mars, if you believe Elon Musk, is 2026 to 2028. And if you believe the NASA timeline, you're looking at 2033 to 2040. So, given the fact and the complexity of your mission, that you will not be returning samples to Earth, conceivably until after humans are already landed there, how do you handle that? And if, by the way, humans do get there about the same time, is there a methodology in mind to have them check out the system and participate in the launch to get this material back?
Right. Great question. I have one answer for you. I would refer to aspirational timelines and look at history of those. So I'm betting that we still get our samples back before humans are there. The second point is one that was made by the Planetary Protection Officer at NASA a few years back at one of our workshops. And by the way, if there is a a nexus and a connectivity, it's the Affording Mars workshops or the Achieving Mars workshops. We're definitely talking to each other at those things. And I'm sure within NASA, Doug would tell us there's a lot more interplay than you might think. But the point was made by the Planetary Protection Officer, at that time at least, that she would not approve of any human landing mission until she saw the Martian regolith in one of these labs back on Earth to prove to her that there wasn't going to be any kind of widespread biological microbial life on Mars before we have human biomes get up there and pollute it. So I'll just throw that out as another potential problem for the people who say they're going to get there before we do. Anybody else want to comment? I'll be the bad guy.
And that's a great place for us to say thank you to this amazing panel.